Hello, MAT225 students. It's Dr. Harris. First of several videos that I'll be recording over the coming weeks. I expect them to be reasonably short overall, and I would expect them to maybe occasionally have mini lectures, but also worked examples. So this one is just going to follow up with a couple of more examples involving the numerical integration techniques that we discussed right before the break. So I wanted to get a couple more examples in front of you and then let you try maybe to do a problem or so before we get together a little bit later this week via video conference. So just want to remind you that what we're trying to do here is we're trying to come up with ways to approximate the values of definite integrals when we don't have a means to find an antiderivative and apply the fundamental theorem of calculus. The three methods that we discussed before the break were the midpoint rule, the trapezoid rule, and Simpson's rule. And I've got those three formulas here at the top of this document that we're looking at right now. And in all cases, we're saying that the definite integral is approximated by the values of these sums. And so m sub n is going to be our midpoint approximation, t sub n our trapezoid approximation, and s sub n our Simpson's approximation. And you can see that in each case, we're multiplying by a multiple of the width of the interval. We're multiplying that by a sum of values of the function, or a weighted sum of the values of the function. So in the midpoint rule, remember that the first step is to calculate the midpoints from the endpoints of our subintervals. And so we calculate our midpoint, we evaluate the function at that midpoint, then we move on to the next midpoint, evaluate, and so on. So we're going to add the values of the functions at the midpoints. Those are the heights of rectangles. And then we multiply them that sum collectively by the width of an interval. This will give us a rectangle approximation. And as I mentioned a while ago, this is essentially something that we talked about almost on the first day of class this semester. The trapezoid approximation uses trapezoids to approximate the areas of trapezoids to approximate the area underneath the curve. And so we saw that what winds up happening is if you use the formula for the area of a trapezoid, you wind up counting the value of each function on the interior twice, and the value of the function at the exterior, the two endpoints of our subintervals, those get counted once. And the 2 here in the denominator comes from the area formula for a trapezoid. The area is 1/2 times the sum of the values of the bases times the height. And then the Simpson's approximation, I didn't discuss this in class when we last met in any real detail, but what we're doing is we're actually using little parabolic arcs. We're replacing the curve with parabolic arcs, and it turns out that if you looked at just the points x0, x1, and x2, the value of the area underneath the parabolic curve that passes through x0, f of x0, x1, f of x1, x2, f of x2 is 1/3 times the width of the interval times f of x0 plus 4 times f of the middle endpoint plus f of the right endpoint. And so this 2 comes from the fact that we would wind up having an f of x2 plus 4 f of x3 plus f of x4 to come up with the area underneath the second parabolic arc, etc. And so the two formulas for the trapezoid and Simpson's rule look a lot alike. We multiply by 1/3 in Simpson's rule rather than 1/2. And because that, we need to weight some of the values a little more heavily. And it's the heights at the odd numbered subinterval endpoints that get multiplied by 4 rather than 2. And so you've got this alternating 4, 2, 4, 2, 4, 2, 4 sequence in the middle. You can see I've got the ellipses here to indicate that I'm leaving some things out, but the pattern continues in the method means that you see. And just a reminder, it's important for Simpson's rule that we have to have an even number of subintervals for that to work. Generally speaking, we'll just use an even number all the time for all of our approximations. So I wanted to just briefly go through a couple of examples. One, here's an integral that we can't evaluate using the fundamental theorem of calculus, the integral from 0 to pi, 4 of sine of x squared. And this is going to illustrate what we get using the midpoint trapezoid and Simpson's rules with n equal 8. I'm going to include some pictures of screenshots from my calculator on Canvas that go with this problem. So go there to look and check those out. So I'll be referencing those perhaps here as well. So delta x in this case, if I'm using n equal 8, the length of my interval is pi. So pi over 8 is going to be delta x. So these are my interval endpoints. To find the midpoint approximation, we need to find the midpoints of each of the intervals. So the midpoint from 0 to pi over 8 is going to be pi over 16. The midpoint of the interval from pi over 8 to 2 pi over 8 is going to be 3 pi over 16, etc. And so I'm going to get odd multiples of pi over 16 as my points to evaluate the function. And so you'll see, if you look on Canvas, that I've got at least the first few values for the function at odd multiples of pi over 16 in the table. And so the midpoint approximation is delta x times the sum of the values of the functions at those midpoints. And we wind up getting almost exactly 3.27 for the approximation. While I'm thinking about it, I'm also going to include a screenshot of the graph of this function on Canvas. You can certainly generate that yourself. You'll see that the function takes on both positive and negative values. And we can see that at one midpoint, that the value is almost as small as it can be. Remember, this function is going to take values on between -4 and 4. And so in this case, the value of the function right here, this must be at 11 pi over 16, is almost exactly -4. Moving to the trapezoid rule, I'm just applying the formula directly. Delta x over 2 times f of the first endpoint plus 2 times f of the second endpoint plus 2 times f of the third point, etc., 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 leaving out a couple of terms here in the middle. Again, I'll have a screenshot of the values of the function at the points 0, pi over 8, 2 pi over 8, 3 pi over 8, etc. But delta x over 2 turns out to be pi over 16, f of 0 is 0, and then I've just applied this formula to the function values that we get from our calculator. Again, I'm rounding to 6 decimal places throughout, except at the end I'll round to 5 decimal places. And we see we get a rather different answer here in this particular case. There are 2 values where the function takes on negative values. I guess that's 5 pi over 8 and 6 pi over 8. So we get 2.76. And then finally, for this example, the Simpson's approximation, we get delta x over 3, and then I just replace the 2's for the odd numbered endpoints with 4's. And so I wind up multiplying some of these numbers, outputs, by 4 instead of 2, and I'm dividing by 24 instead of 16. And you can see I get a rather different answer again, 3.347, roughly speaking. So this is an example where we get a great deal of disagreement among our 3 approximations. And the primary reason for that is that if you look at the graph of the function in the second half between, say, pi over 2 and pi, we're starting to get some wild swings in the value of the function. And that's going to happen more and more. If you extended the graph beyond pi, you'd see that the function starts swinging more rapidly. And so that just means that if I don't take intervals that are very narrow, I'm going to get rather different values for my function. even the different weighting between Simpsons and trapezoid is going to give me some possibly different values. And so we would get a better approximation by taking n to be larger here. But for the moment, we're just trying to get used to applying the formulas and recognize that we may wind up occasionally, especially when we have these rather sudden changes in the value of the function, some rather different estimates. First example that we worked in class was much more stable in that regard, but that was a smoother curve. Next, I want to look at another type of example where we're actually not given a formula for the function, but we're just given straight values for the function. This is a problem that I found in another calculus textbook. And the instructions are to use the trapezoid rule to approximate the area of this supposed area of land that's next to a lake. And so what they've done is they've measured the distance from the back of the property to the lake at 10 feet intervals. So we want to recognize that this, since there are 8 strips here, that must mean that the lot is 80 feet wide, and we're taking measurements every 10 feet. And so, as in the previous example, n is going to be 8, and we want to recognize, since we're taking measurements every 10 feet, that delta x is 10. So I'm letting h of x be the height of the lot from its back to the lake, and we're moving from left to right as per usual. And so according to the trapezoid rule, I want to recognize that these are the values of my function. I don't need a formula for this curve up here if I know the heights. And so according to the trapezoid rule, the integral from 0 to 80 of h of x dx is going to be 10 over 2, which I've written here is 5. And then I just take the heights, I multiply the interior values by 2, and multiply the 2 endpoints on the end just by 1. And I punch this into my calculator, I get that the lot has approximately 4,570 square feet. And just for kicks, I've gone ahead and applied Simpson's rule as well. And delta x is still 10, so I get 10/3 out here. And again, I'm replacing some of my 2's with 4's. When I multiply all this out, I get a number that in this case is somewhat closer in value to the previous approximation, 4,566 2/3 square feet. So at this point, I'm going to end here. And so I hope that if you have any questions about this, that you'll ask them when we get together to talk via video. I'm also going to be asking you in an email soon to work a problem and try to upload it through Canvas just to make sure that we can do that sort of thing. So looking forward to talking with you soon.